5 seconds of silence. We're going to explore a new theory called causal memory gravity. And to do that, we'll start with a fundamental crisis in cosmology that makes a new theory necessary in the first place. Then we'll dive into the core idea, the concept that spacetime itself has a memory. We'll look at the math behind it and the real-world tests it's already facing. Finally, we'll touch on its most profound implication, that everything in the universe might come from a single source, and see where this theory stands today as a piece of science in progress. Our journey starts where so much of science begins, with a problem, a really big one. You see, modern physics rests on two great pillars. There's quantum mechanics, which describes the world of the very small, and then there's general relativity, our theory for the cosmos. The problem is, when we look out at the universe on the largest possible scales, the predictions from general relativity, well, they just don't quite match up with what we actually see. Right here, in our own cosmic backyard, Einstein's theory works beautifully. It's a staggering success. It predicts everything from the way an apple falls to the strange orbit of Mercury, even the way light bends around a black hole. But when you zoom out to the scale of galaxies, it starts to look broken. Stars on the outer edges of galaxies are spinning way too fast, as if something invisible is holding them in place. And when you zoom out even further to the cosmic scale, you see the universe's expansion is actually speeding up, pushed by some mysterious force that the theory just can't account for. Now, the standard explanation for all this is to invent two new things, dark matter and dark energy. These are mysterious substances that supposedly make up 95% of everything. But here's the catch. We've never actually detected them. Causal memory gravity suggests there might be another way, a path that's maybe more fundamental. What if the problem isn't something in spacetime, but spacetime itself? This new theory challenges one of the core ideas of general relativity, that spacetime just instantly reacts to matter and energy. Instead, it proposes that spacetime isn't perfectly springy. It suggests that spacetime holds on to an imprint of what's happened before, that it has a memory. So how would that work, a memory in spacetime? Well, the idea is based on a completely new picture of what spacetime is at its most fundamental level. It's called the dynamic Planck network. The theory says that if you could zoom into the smallest possible scale, the Planck scale, you wouldn't see a smooth, continuous fabric. Instead, you'd find a network of tiny, interconnected nodes. Now, here's the key. A discrete network like this can actually store information in its structure. Every node, every connection holds a record of what caused it to be that way. And this collective evolving history, that is the memory of spacetime. Think about it this way. In general relativity, spacetime is just a passive stage where the play of the universe unfolds. But in this new picture, spacetime becomes an active participant. It's a dynamic medium whose very structure is being constantly rewritten by its own past. So what happens when this memory builds up over billions of years, over the entire history of the cosmos? It creates a large-scale effect. It's called a dynamic memory condensate, and what it does is change the way gravity works over vast distances. It's this emergent property, something that grows out of the tiny network, that we perceive as the accelerated expansion of the universe. Suddenly, you don't need to invent a mysterious dark energy to explain it. But of course, a compelling story isn't enough in physics. To be a real theory, it needs a solid mathematical foundation. And here it is. This is the core equation of causal memory gravity. Now, you don't need to be a mathematician to get the gist of it. It starts with the standard math of general relativity. That's what the R represents. But then it adds a new piece. And that extra term, that is the mathematics of spacetime's memory. So let's break this down into its basic ideas. First, the source of the memory is simply the curvature of spacetime itself. Anytime spacetime gets bent or warped, it leaves a trace. Second, there's a rule, represented by REIT, that enforces causality. It's simple. Only the past can affect the present. And third, there's a dial, a single parameter called eta, that lets you control just how strong this memory effect is. And here's what makes this so powerful. If you take that dial, eta, and you turn it all the way down to 0, the memory effect vanishes, and the equation becomes exactly the same as Einstein's general relativity. This is so important. Causal memory gravity doesn't throw out Einstein's theory. It builds on it. It's a conservative extension, with general relativity built right inside. The theory also has built-in guardrails. You can't just set the memory parameter, alpha tilde, to any value you want. For the math to be stable and physically realistic,
For it to be free of weird instabilities that we call ghosts, that parameter has to fall within a very specific, narrow range. It's a key constraint that keeps the theory honest and well-behaved.
So, the theory is mathematically consistent, but elegance isn't enough. The real question is, does it match reality? To find out, we have to put it to the test. And causal memory gravity makes some very specific predictions. It says that the weird rotation of galaxies isn't caused by invisible matter. It's a memory effect. The theory also naturally explains a known pattern, the tight link between a galaxy's mass and its spin speed. On top of that, it predicts unique signatures in how large structures in the universe grow over time, and even specific changes to how we measure the distances to exploding stars. And these aren't just tweaks to fit the data we already have. They are genuine, falsifiable predictions about how the universe should look.
And recently, the theory faced its first big test. Scientists used public data from a major survey called the Dark Energy Spectroscopic Instrument, or DESI, to check how cosmic structures have grown over time. They were looking for any deviation from general relativity. A value of 1 would mean perfect agreement with Einstein. The result they got was 0.995, plus or minus a small error. In other words, it passed. Causal memory gravity is entirely consistent with our best current observations of the universe. But of course, one test isn't enough. Science demands more and more precise checks, and that's exactly what's coming. The next generation of telescopes, like the Euclid Space Telescope and the Rubin Observatory, are going to map the cosmos in staggering detail. Their data will provide the decisive tests, the ones that will either give powerful support to this theory or potentially rule it out for good. Now, if this theory turns out to be right, the implications go way beyond just explaining gravity. And this might be its most profound idea. The theory suggests that this dynamic Planck network isn't just the source of gravity, it could be the single fundamental substrate from which all of physics emerges. That means not just gravity, but electromagnetism, all the forces, all the particles, they could all just be different kinds of vibrations or collective modes of this one underlying network. And there's already some early mathematical evidence for this. When you analyze the vibrations of a simulated network, kind of like its spectral fingerprint, you find something remarkable. The ratio between two of its lowest energy vibrations is a very specific number, 3.925. And that number is exactly what you'd expect to see from a process that gives rise to a long-range force. This emergent vibration is identified as the photon, the particle of light itself. So it's crucial to be clear about one thing. Causal memory gravity is not being presented here as some final proven fact. What it is a legitimate, active scientific research program. Its ideas are published in peer-reviewed papers. It makes concrete, testable predictions that are right now being checked against real-world data. It's a framework built to be challenged, to be tested, and maybe even to be proven wrong by the evidence. And that is the very definition of science. So, we're left with this compelling new picture of the cosmos. One where the great mysteries of dark matter and dark energy aren't new things we have to find, but are simply the echoes of the universe's own history, written into the memory of space-time itself. Is this how reality actually works? That's a question for the universe to answer, and for our observations to hear in the years ahead.